This is a brief coverage of Chapter 6 in CIST 2451. We are looking at the network layer in this chapter. The network layer has got four things that occur on it. Number one is we address the end devices. We're going to use IP addresses there, and those are the number addresses that we will assign to the devices. Encapsulation will occur on this layer. With encapsulation, we will be taking the segment from the transport layer and then adding more information around it, including the source and destination IP address, a checksum value, some other header information, and creating a new protocol data unit, or PDU, called a packet. So we're going to be dealing with packets in this chapter. And then routing occurs on this layer, and so the device we will be working with on this layer are these routers. And that is that it's going to provide the services on this layer to direct our packets from one router to the next router to go from the destination to the next destination, but it's going to be going from the one point to the next point in terms of getting all the way there. So we're looking at the paths of what's the best path to go from where we are to where we want to get to. De-encapsulation or decapsulation, and decapsulation is a term you normally see in most books out there and the term that Cisco previously used, but in this book they've come up with de-encapsulation. Just says the opposite of encapsulation. Encapsulation says we take the segment and add more information around it, create a new PDU called a packet. In de-encapsulation, we're taking the packet, removing the extra information that was around it and coming out with just a segment, and then passing the segment on up to the transport layer. In encapsulation, we're taking the segment from the transport layer, adding information around it, making it a packet, and passing it down to the data link layer. So those are the four major areas that items we're going to do on this one. We are going to be working with different protocols on this layer. There's 5 of them listed in the book, and I'll talk a little bit about 4 of them, and the 5th one I'll mention very briefly. The first 2 actually are the same protocol, just different versions. There's IP version 4, which is what we've been using up till now, and then there's IP version 6, which has been around since around 2000, but is just now really getting extensively used, and we're finding it more and more used now, and I suspect within a few years that'll be the extensive one used out there. But right now still IP version 4 is the extensive one out there, and we'll look at some of the characteristics about IP version 4 and 6 in just a little tiny bit and see why we want to move from IP version 4 to IP version 6. But IP version 6 came about in about 2000. IP version 4 dates back to about 1980. But those are the 2 most common ones. They're the ones that the internet runs off of, and everything runs off the internet now. So guess what? They use the internet protocols, and specifically on the network layer, the internet protocol. 3 others that they also mentioned that aren't as widely used now, although 2 of them were extensively used in the past, and so you may see mentioned or hear people mention still today. The first one is IPX, which is Novell's network layer protocol. Notice it ends with an X, and you'll notice that most of Novell's all ended in X's. So if you see a protocol that ends in the letter X, you can guess that it belonged to Novell. Novell was the predominant network provider out there until we got to the late 90s. And so IPX was extensively used there up until the mid-90s. It's not very often used anymore. Novell, when they moved to version 5 of their operating system, network operating system, they went to IP also. Apple had their own out there that they used for years till about the same time period as Novell ceased. As we all moved onto the internet, everything moved over to IP at that point. But Apple Talk was the one that Apple used. Talk was what Apple tended to use as the last part of the names of their protocols that they created, and both Apple Talk and IPX are both proprietary protocols. IP is not a proprietary one, but is an open standard. And then the fifth one they mention is CLNS, or Connectionless Network Service, which is actually used in telecommunications. And other than seeing it mentioned in this book and this course, you probably won't run into CLNS out there. And that's the extent that I've ever dealt with CLNS, is just where it's been introduced in this course. They mention some characteristics about IP and give you three major basic characteristics on IP, which is things for it. One is it's connectionless. What that says is that it does not see if the destination is there before it sends out the data packets. It ships them out onto the internet, and we assume that the area is there on the other end. That's similar to how you mail a letter. You actually use a connectionless system to sending your letters out on the internet, also out on the post office. You drop the letter in the post office box. You don't know for sure that that address is absolutely correct always that you've got on there when you mail it, but the assumption is it is, and that it goes ahead and tries to send it. Now, that also means that it's best effort and unreliable. That IP takes it and tries to deliver it to the location that you specified. Just like with that letter that you mailed at the post office. It's best effort by the post office. It may or may not get there. If the destination is there, it should get there. Now, in the post office example, there is a connection-oriented approach, and if you sent it with, you registered it, you'd know that it did get to the destination. In networking, there are protocols on the other layers that will make sure about the delivery and stuff. And it's media independent. IP works across any type of media. So it will work on fiber optic, copper, and wireless. So it works real well in that approach. The IP version 4 packet, they give you some descriptions about it, give you some basic setups on it, tell you about that it has a header and the payload. The payload actually has the segment, which contains the actual data. And then on the header, that it adds in there a version number on it so that we know we're using IP version 4. It has something called differentiated services. It used to be called type of service, and that's a way to prioritize the packets out there, although that's not used real often on it. Time to live is one that you ought to be well aware of. Time to live says that when this packet's sent, we put a time to live value on there. Typically, that has been a number of 15 or 31, 31 more often than now, but each time it passes through a router along the way and that packet gets rebuilt, it subtracts 1 off the time to live. When it reaches 0, that router then just drops the packet and it no longer exists and it just disappears. If we didn't use time to live, packets would be out there congesting up the internet forever. And so it's a way to keep things that don't have a correct destination on them from just sitting out there devouring everything everywhere. Some of you may have heard the stories about the alleged story of the man getting caught inside the subway system in New York or Boston, and that didn't have the money to pay to get out at the end, because there on their subway system you pay to get on and then you pay to get off at the end also. And that he was stuck forever in the subway system because he couldn't get out because he didn't have that amount of money. Time to live is a way to stop that from happening. That after so much time of him being on the subway system, if he'd had time to live, he would have been automatically let out. Another way to look at time to live is that you as a human don't have a time to live value. That would have been stamped on us at time of birth, and we'd know exactly when we're going to die. That we would have been told we've got X number of days we're going to live in our life. Instead, we know that there's going to be some point we're going to die at, but how long we're going to live, we're not sure. That we may live for 70 years, 90 years, 100 years, maybe only 50 years, but hopefully we all manage to have good long lives. Protocol value in there just tells us what protocol that the data is using on it, and that's back in the segment part, and then it's got a source IP address and a destination IP address. And those are 32-bit fields in IP version 4. Those are the numbers that you see that look like 192.168.4.1, What that is each of those values is 1 byte long. Each of those 4 numbers can range from 0 to 255. And so that's all on there. There's a total length value on there also. There's also a checksum value, which is a way to make sure that the whole packet did arrive. It calculates a value and sticks a number on there based on its calculation, and when it arrives at the other place, it calculates the number again off the packet, compares it, the number it came up with the number that's in the checksum. If they're both the same, it assumes that it was reliably delivered, that it did all arrive intact. But if it doesn't match, it just discards the packet. It just ignores it and throws it in the trash, basically. IP version 6, like I say, is really catching on now. In the last couple of years, you've seen it coming on more and more dominant out there. All of your network equipment now that you buy is all IP version 6 compatible. If you've got some older stuff that is 17 years old, it may not be IP version 6 compatible. Problem with IP version 4 was that there was only about 4 billion addresses available, which when they created it back in 1980, before anybody envisioned where the internet would be today, or the World Wide Web hadn't been invented, which is what really took off everything. They thought they had invented something that they had plenty of addresses forever on. Well, now they had no vision of everybody having multiple devices that all had individual IP addresses, and then that we'd have even devices in our homes and everything else. For instance, that you can now hook up to your home to where you can turn the heat up or down, turn your security system on or off from somewhere else, check the cameras in your house, lock the doors, etc., all across the internet. Guess what? Those all need IP addresses to do that. Your phone, because it works on the internet, requires an IP address. Your desktop computer, your laptop computer, your tablet, any of the others, you're needing them. So you've got lots of them that you need. Back in about 1999, we originally were running out of IP version 4 addresses, but we started using NAT at that time, which is network address translation. And that with NAT, N-A-T, it gave a way that we could use a group of addresses that aren't recognized on the internet, and there's groups of them we'll see in the next chapter that are set aside for special purposes that we can use for just in a private network, not one out there for the public use. And the 192.168 address range happens to be one of those ranges on it. That you could use those, and they can be used over and over again out there, but they can't be used on machines that are actually directly connected on the internet because they're not unique addresses. But with NAT, we can have an address on our router coming in, and then once it comes in there, that NAT will have a NAT host there on our router, and it will turn and change the address that came in, look at it, and it realizes which machine it belongs to because it keeps a way to keep track of it. And it'll change it to the address of the machine inside our network and send it to the correct machine. When you go to send something out, it has that address that's not recognizable on the internet on it. It gets to your router to go out onto the internet. It switches the address to the address of it, a real one, but it remembers what it was, so that when the response comes back, it knows which machine to send it to. And that works real nicely. And that extended our use of IP version 4 addresses for years. However, about a year ago, in February of 2013, I believe it was, that we actually did start running out again of IP version 4 addresses, even with the fact that many devices don't use those addresses. They have to use individual personalized addresses. And so we've run out again, and so we're now moving rapidly into IP version 6. IP version 6 is based on a 128-bit address instead of like IP version 4, it's 32 bits. That's 4 bytes, which are 8 bits each. And so our number of addresses increases from just over 4 billion to 340 undecillion addresses, which the book says is equivalent to every grain of sand on the earth. But in any event, it gives tons of addresses for every individual out there. So we don't envision running out of these addresses in the future, but that doesn't mean that we won't, because exactly what can be done with the internet and what we are doing networking wise, who knows in 20 to 30 years, who would have guessed back there in 1980 about the World Wide Web, and about people would be walking around with phones on their belts that had full computer capabilities, that actually had more computer capabilities than the mainframes that they were working with at that time. So we don't have to use NAT anymore with it. We can assign a unique address to everything out there. We don't have to have things that have just specialized addresses within the network, within that network, but not out there publicly. And that it does give us an increased ability to secure our information across the internet also. But it does mean that our packet header will grow in IP version 6, so it's going to be a bigger one now. It's got a little bit different things on it, but most of it's the same type stuff. It does have a hop limit now on it instead of a time to live, but it's the same thing as time to live. A hop is just when you go from one router to another router, and from another router to another router, and that is drawn as lines going up and down like that. And so it's like a rabbit hopping along, and every time the rabbit hits the ground, it counts as one hop. And so we're going to be working with routing on this layer, and that when a packet comes into a router, it's going to look at it and look at the IP address and see, where does it belong? Does it belong on this router, which would be where it's got a special address addressed to something on the router itself, which are loopback addresses. You see it referred to as a loopback address usually. And that address in IP version 4 was 127.something.something.something, although you usually see it as 127.0.0.1. There's one of the inefficiencies of IP version 4. They went and set aside that ton of addresses right there just for something that you only use at most a couple of those loopback addresses. So they had a bunch of them. If you want to find out if your NIC or network interface card is working on your machine, you could ping 127.0.0.1, and if it comes back, you know you can make contact with your network interface card. So it is a useful one on it. In IP version 6, the address for that is ::1/128. That's the only IP version 6 address I can tell you right off the top of my head. Localhost is a packet that is being sent to some device that's on the network that's connected to that router. And so it knows it just got to put it onto that network, and that the host is sitting right there. And they've got the same network address. And then a remote host is where it's something sent to a host or a device that's on another network, and so it's got to figure out a route to send it in and which way to send it out of the router. The router is merely a computer that has 2 or more network interface cards on it. Now actually that means that in a case of a lot of your laptops and even some of your desktops, technically they're routers also, because guess what? You've got a wired network interface card on them, and you got a wireless network interface card on them, and you can actually do routing on them. However, when we usually look at routers and talk about routers, we're talking about specialized computers sitting there that are real simple computers. They're stripped down. If you were to look at how much memory was in them and stuff, that you'd go, there is no way I can work on a machine that's that limited. They're back to 1980s standards in most cases. But they're just working with a text command line interface on them, and that they don't require much memory or storage space on them. So you'll have them there with that, so that you've got that for them. However, they do tend to cost more because they're designed to handle network traffic better on it. If you're looking in the router, if you're looking at a routing table, you will see an entry in it sometimes as the network destination of 0.0.0.0. That's also called quad 0. That is where it's saying that's the local device on it and about what is our gateway to get out of this. What is the way out of this machine out into the real big world? And so that's just your exit off your router, essentially. Or if you were thinking about a fenced-in backyard, that's the gate out of it going out into the real wide world. And that's your gateway. And that on the router in Cisco, you'll actually put in your entry for what the gateway, the default gateway is, using quad 0 followed by the address of the interface that goes out. On your PCs, you're going to do it in your GUI in Windows, and that it's one of your entries, the bottom entry down there that asks what is the default gateway, and you'll give it the address that tells it what is the address to get to the router to get out of the network. How do we get out of this network and get out into the real world? So that we're not stuck just inside our own little network. And so they show you that. They mention that if you want to see the routing table on the PC, you're going to use the command netstat-r, and it'll give you the routing table. In the Cisco router, you're going to use a show command, and remember your show commands. Show command is extremely important to you. Show run, you've already been introduced to you, which shows you the configuration, and that you can see how is it configured at any time just by doing show run. Show IP route will show you your routing table in your router or your switch. And so show IP route is an important one for you on that one. And then they mention that you can look at some other things. They also mention about on your routers, what's inside a router. A router does have an operating system. It is a PC. It is a computer there. On Cisco routers and switches, they're using the Cisco iOS for their operating system. It's got a central processing unit or a processor or a CPU in it. So it does have a brain to it. It's also got random access memory or RAM in it, built in it. So it's got RAM just like you do in your regular PCs, except it doesn't have the amount of RAM you're used to. Y'all are all used to having at least a gig of RAM, and probably in terms of 4 to 8, 16 to 32 gigs of RAM on your PCs nowadays. It also has read-only memory, which is where it has the basic information to start it all up from, just like your PC and your phone and all the others do, that tells when the power gets turned on about where to go look for the operating system. And then it's got NVRAM or flash memory. That is where it actually stores our configurations, and that will be storing our configuration in there, so that when you copy run start, you're actually storing the configuration you've been working on into the flash memory at that point. RAM is volatile. That means that when the power gets turned off, it disappears. Your brain is volatile. When you die, everything that's in your brain disappears. What we write down on paper is non-volatile. It stays on, or recordings stay on. When I die, that assuming we still got internet and everything else out there and got ability to look at videos and things, that you could still go back and look at this video again and see what did Dr. Watt think about Chapter 6 and CIST 2451. Because that information will still be there. It's non-volatile memory. But what's stored in my brain, what I haven't written down anywhere, all disappears at the time I'm dead. So ROM is non-volatile memory. Flash memory is also non-volatile. And so we're going to have that. And then your startup configuration file gets stored in NVRAM, which is non-volatile RAM. And that is part of that out there also. The operating system is stored on flash memory, and it's easy on that one. And they go through and describe a few things about what one of their routers look like, and if you were to look at other brand routers, it would be the same type of information. This has been a brief overview. Oh, the last thing is, when you're setting up your ports on your router and your switch, there's one command. You got to tell it what the address is, and you also have to tell it subnet mask, and we'll look at subnet mask in the next chapter. They give you the subnet mask in this chapter. But subnet mask is going to tell us of that IP address we've got, what part of it is the network and what part is the host, because it contains both the network and the host. It's sort of like that your address where you live of combining your street address with the city-state all into one word, and that knowing where to split it to know which part is the city, is the street number versus the city-state of which city do we live in versus which house specifically in that city do we live in. But the other part is that some of you don't sometimes catch right on is when you set up that port on it, that you also have to enter a command at the end after you've done the address on it, and you may have also done a little other information on it. You have to do no shut. No shut is a double negative. I realize that. Don't tell your English teacher I'm teaching you to use double negatives, but that's the way Cisco wrote it in their operating system. No shut's really start. It's saying is to unshut down the port. The ports are shut down by default, and so by doing no shut, you're saying start the port. It would be sort of like, instead of me telling you to go over and turn the lights on, me tell you to no off the lights, which is saying turn on the lights. So turn no off the lights is saying turn on the lights. Well, turn on the lights makes a whole lot more sense, but in Cisco, you have to turn on the port, and you use no shut to turn on the port. This has been a brief overview of Chapter 6 and CIST 2451, presented to you by Dr. Watt. Please read over the chapter. If you have any questions, send me a message and ask questions to me. Also use your discussion board and ask questions, and I'll be glad to answer and provide you any additional information on it and to describe things further. Hopefully this is a help to you, and good luck with the class.